Hello, and welcome back to a video series on MAC 1105 College Algebra. My name is Sean Perry. These are guided notes number 10 in the series on section 3.2, the graph of a function. The first series of questions is going to deal with the domain of a function. Now, the domain are the x values that we are allowed to plug into a function. For a great many functions, that's going to be the entire real number line, although we could imagine only whole numbers being plugged into a function, or wider than that, complex numbers being plugged into a function. For the functions that we're going to consider today, we can establish that their values should be real. Any real number off the number line we can plug in unless some problem occurs. And right now there are two problems you need to be aware about. Number one is that division by zero is an undefined concept. It causes huge problems if you allow this collection of symbols to have meaning. And so we leave it without meaning. It is a nonsense statement that does not actually become defined in a mathematical system. And as such, if I have a function like 1 over x, I have to make sure that this x value is itself never 0. 0 would not be an element of the domain of this function, even though 0 is a real number. Likewise, we want to restrict our outputs to real numbers. And so we don't want to plug any numbers into a function which would produce something else besides a real number. Well, right now, one of the only ways that you know that we could break out of the real numbers is by considering the square root or the even indexed root of a negative. If I took the square root of a negative, I would wind up with a complex value. If we want to make sure that these numbers are real values that we get back, we need to also say that any square root or even indexed root should be non-negative. It should be positive or 0. However, when we look at certain functions, we're going to see that there really aren't either of these two big rules that we have to make sure are followed. For example, in this line, which is, yes, a line, if we distribute this 6, we get something that looks like mx plus b, then we really can take any number from the real number line and plug that in and get, well, 9 times that is a number, minus 16 is a number, and divided by 6 will just give me a real number back. And so there is no domain restriction on p of x. Its domain is the entire number line, which we write in interval notation this way. Likewise, with s of x equal to 3x plus 16, we're dealing with a line. There are no numbers that I can't multiply by 3 and can't add 16 to, and so the domain is, again, negative infinity to positive infinity. Even in the case of polynomials, the domain is still going to be unrestricted. There are no numbers that I cannot simply take a power of them and add them to constants times other powers of those variables. All polynomials, including this quadratic polynomial here, have a domain of negative infinity to positive infinity. Here we find ourselves with a function that actually requires a domain restriction. That's because we're dealing with a square root, an even indexed radical. And as such, we need to make sure, if we want our outputs to stay real valued, that the inputs cannot be negative. So we ask the question, where is x minus 1 greater than or equal to 0? Well, solving, it's precisely where x is greater than or equal to 1. And so this is our domain. We can see why this is an important restriction to make by looking at a graph of this function. Here I've plotted the function on Desmos, and we can see that the curve doesn't appear to have any values when we go below 1. There are values here, but they're actually complex values. And what we've done is plotted a real number line x against a real number line y. And so these complex values do not appear on our graph. Here we have a more complicated situation. We have a rational function. We have a ratio of two polynomials, 1 over x squared minus 4x minus 32. Now, the main idea is that the denominator of such a function is not allowed to equal 0. So we have to ask, what are the x's such that the denominator would be equal to 0? And then we need to omit those values. So first, let's solve that equation. When is this expression here equal to 0? For what values of x? Well, factoring, fixing our signs and looking for factors of 32 with a difference of 4, we find the following two solutions for x. And so what we've learned is that we must forbid these values to go into the function g, because if we allowed them to go in, we would get a 0 in our denominator, and such a thing is undefined. So how do I write in interval notation that x mustn't be equal to 8, nor can it be equal to negative 4? Well, the main idea is that we want to go up to our lower of the two values and omit it using parentheses and unions. This says go up to -4, exclude it, and then start again after -4 and go up to 8. We exclude that as well and go up to infinity. And so here we have our answer in interval notation. All of the x's are allowed to go into this expression except for 8 and -4. It's nice to look at a graph and see what exactly is happening at those forbidden values. At those forbidden values, we would be dividing by something that was, well, at them we would be dividing by 0, and so -4 and 8 must be omitted. But your eye can probably pick out that there's something bizarre going on at those two locations in this graph. What will happen is as we approach -4, we'll get closer and closer to 0, and so this reciprocal becomes very large, either a large positive or a large negative number. The same thing is going to happen near 8. If we get close to 8, our denominator becomes small, and so we either get a large positive or large in magnitude negative number. And so it seems to shoot off towards infinity in a split kind of way. At those values, the function is not defined. There isn't actually a value there at -4 or 8. No real value anyway. Here we have a simpler expression of the same idea. I need to make sure that this denominator is never 0. How do I do that? Well, I'd like to find out where it is 0. It will be 0 when x is equal to 15. And the idea is that we want to omit this value. We must have it so that x is never 15, because plugging 15 in here would give me an undefined expression. So how do we omit 15? We start from -infinity and go up to 15. We exclude it with parentheses. We union that, starting just after 15, going up to infinity with this interval here. And that total expression will give us the domain of allowed values for this function. Okay, moving right along, how can we use a graph to determine domain and range? Well, remember that our domain is going to be our used x values and our range our used y values. So let's take a look at the domain here. We are going to have something going on at 2, and all of these x values as well. If we look above, we see parts of the curve above there. That means that there's a y value assigned to all these x values, not this one. This one has an open circle, which means that there isn't actually a defined value there. And then this arrow means that it continues on forever in this direction. So this line that I've drawn are the x values that will be used. How do we write this as an interval? Well, this goes from -infinity up to -3. It excludes -3 and then continues up to 2, and then it includes 2. What about the range? Well, let's see. We just need to look at each y value and see, is there a corresponding x value which would give me that y value? And we can see, starting at the topmost value, there is a value which would give me 4. This crest could be interpreted as hitting 4 as a y value, and so we will include it in our range. Going down and looking left and right, I see some curve on the left and right, and so we will include all of these values in our range up except for this one. We won't include -5 because, again, this is an open circle that shows that we're not including that point, and so we don't want to include that in our range. To finish this problem, though, we need to consider this arrow here, right? This actually looks like a line, and the arrow tells me that it goes on forever and ever 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 and so on, right? So what is actually going to happen? We're eventually going to get bigger than 4 again and continue ever upwards with our range. So actually, even though in the first part of the graph, it didn't really look like we were going to include values greater than 4, this arrow, right? This arrow here tells me that the line will continue on in this fashion. And so now we really need to look back at our interval and say, well, what y values really did get hit in the end? Starting from a lowest value of -5, but not including it because of this open circle, we're actually going to rise forever. And that is our range. If we had stopped right here, we would have stopped at 4 and included it. But since we rise forever as part of this line, we're going to include that section above 4 as well, because it will eventually get hit. This next question is going to require us to know a little bit of lore about this shape. This shape is called a parabola. And something you need to know about parabolas, coming from functions which are quadratic polynomials or having to do with squares is that any x value can be squared. And as such, this parabola is going to widen forever. It might get arbitrarily steep, but it's also going to get arbitrarily wide because there's nothing preventing me from squaring big numbers. So what will our domain be? Well, all of the values we can see on the graph, that's for sure, but we need to understand what is being depicted here. This graph continues on forever. It gets both ever higher and ever wider. That is very important for us to extract from this, even though we can't see off the edge of the graph. We have to be able to use our imagination and to understand what's being depicted, which is a squared function, a parabola, a quadratic polynomial, and as such, the domain is going to be from negative infinity to positive infinity. The range, on the other hand, has a smallest value. The range only seems to get as low as -9. -9 is the smallest y value, but it seems to go forever up and up after that. And so as such, our range is going to go from -9 and including it, because it does attain that point, up to infinity. What about our x and y intercepts? Well, our y-intercept, which will be unique, is right here at 5. So we would say the y-intercept is at y equals -5. Likewise, the x-intercepts, which are actually plural, are going to be here and here. And so we have x-intercepts at -5 and 1. Technically, these are, of course, the coordinates 0, -5, and -5, 0, and 1, 0. But since we know all x-intercepts have y value 0 and all y-intercepts have x value 0, we can generally just include this non-trivial number here as our answer. Here we have another function that appears to be a absolute value type function. It's that characteristic V shape. And we don't really need to know that. We do just, however, need to know that this pattern of two lines is going to continue on forever, both going ever up and ever to the left and right. That means that all of our x values, not just the ones that can be seen on the graph, but all the ones we have to imagine outside of the graph, are also going to be hit. Our domain is still negative infinity to positive infinity. And like the quadratic equation we just saw, our range has a lowest point. It doesn't get lower than +4. And as such, our range is going to include all these values. Again, we're going to go up past the edge of the map here, and we need to include that in our range because this function gets ever higher as it gets ever wider. Where is my y-intercept? Right here at 7, where it hits the y-axis. Where is my x-intercept? Well, it actually never hits the x-axis. There's no value at which this thing gets lower than 4, and so there's certainly no value at which it becomes 0. And so we would say that this either does not exist, or we could use the null symbol. Either answer is fine. I sort of prefer this as my symbol for nothing, but whichever your homework stipulates, that's what you should enter. Here we have a function that looks like a section of a parabola. As such, it doesn't go on forever. We don't see any continuation here. We see stopping points. We see that it stops here and does not include this point -3, and that it keeps on going up until it gets to 1 is my highest x value and includes that. So my domain would go from -3 exclusively up to 1 inclusively. What about my range? My lowest value seems to be -5, but it never really hits the -5. So let's treat that with an open circle. All of these points have y values here on the axis, and it goes up and up until it gets to 4. And it seems to include 4. When we see it pass through this way, don't try to overthink this and think, well, is it just getting close to 4? If it looks like it attains 4, it attains 4. And so our range here is going to go from -5 exclusively up to 4 inclusively. Now, what about the x-intercepts? Our x-intercept is right here, where it hits the x-axis at -2. What about our y-intercept? Well, it hits the y-axis at what appears to be 4. And so this breaks down the information about this graph. Continuing with this process, we can see here that for our domain, our x values are going to include -2. All of these x values get used, all the way up to 8, which does not get used. It's an open circle. Likewise, our range begins down here at -1 and includes it, and includes all of these y values all the way up to this highest y value at 9, but not including it. And so our domain is -2 inclusive up to 8 exclusive. And our range goes from -1 and including it all the way up to 9 and excluding it. Our x-intercept is right here at -1. Our y-intercept is right here at +1. And now we're asked for a couple more points. What is the value of f when x is 2? Well, when x is 2, we're right here. We go up to find the y value, which is our value of f, and that looks like it's occurring at 1, 2, 3. Likewise, what about at 1? We have a f of x value at 2. Now we're going to pivot to talking about some concepts called increasing, decreasing, and constant behavior. So as we proceed to the right, as x increases, what does the function do? Does it stay level? Does it get smaller? Does it get bigger? So here we can see that this function is getting smaller as we go to the right along this interval. That behavior seems to stop at 1. So all the way before this, and I guess if we can infer that this is a line that keeps on going all the way before this is all where the x values, where the y values are decreasing as we go to the right. Likewise, over here, we have constant behavior. This is a level line, so it's not going up or down as we go to the right. And as such, all of my values after 1 seem to have constant y value for a given x value. So my constant interval starts at 1 and goes to infinity. My decreasing interval seems to go from -infinity up to 1. And we actually don't see any place on this graph where we have increasing behavior, where we are going up as our values of x go to the right. So we would just say that this isn't an interval. There does not exist an interval on which the function is increasing for this graph. Here we have the same question in a slightly more difficult context. Let's consider, where is this function increasing? So as we go to the right, it's going down. Here it stops and it starts going up. It's increasing in this region. Then it goes down again, and then it's increasing again in this region. Likewise, where is it decreasing? Well, here as I go to the right, the function is going down, and that continues up to this point. Same thing with this hilltop down to this valley. It's decreasing along that interval. And it doesn't seem to be constant anywhere. So let's mark these regions from -6 up to -4, as well as from -2 up to infinity. It seems to be increasing. Likewise, from -infinity up to -6, it seems to be decreasing. And yes, we're going to just infer that the graphs keep on doing what they're doing here, getting wider and getting steeper as they go off the edge of the map. That's how we get these infinities. But where else is it decreasing? It's also decreasing from -4 to -2 for these particular x values. Where is the function constant? It doesn't appear to have any level behavior. There's no place at which it is flatlining, and so we would say that there is no interval on which the function is constant. A related idea to increasing and decreasing is where there is a relative maximum or minimum. A relative maximum or minimum can be found where the function changes from increasing to decreasing or decreasing to increasing. For example, if I am increasing and then I stop and I start decreasing, you can see that this has created a little hilltop here. We call this a relative maximum. On the other hand, if things go in a different order, if we go from decreasing and then we start increasing again, this creates a little nadir or a little valley, which we call a relative minimum. It's relative because it might not be the overall smallest thing on the graph, but it is going to be the smallest in a little window around that minimum. So let's see where this function is increasing or decreasing. We can see it's increasing here, and then it starts decreasing, and then it starts increasing again. What about decreasing behavior? Well, between this hilltop and this little valley, it is decreasing. And that tells us where we're looking for our maxes and mins. Here I have a maximum. The x value at which it has a relative maximum is -5. And the relative maximum itself, the value, is at -6. So when they ask about the relative values of these maxes and mins, that's going to be your y value. The x value at which it has a relative maximum, also called a critical point, is going to be the x value, so -5 for this point. Likewise, what about for the minimum? Well, it stops decreasing and starts increasing at -3. So this x value is going to tell us where to find our lowest local point. And that lowness is given by minus 7. And that's pretty much all there is to that. Let's practice again. This graph has some slightly steeper looking maxes and mins. Let's mark where it's increasing. Let's mark where it's decreasing, here and here. And then this will allow us to find our relative extrema. Now you also could look at the graph and say, oh, well, that's a high point and that's a high point, right? But we can formally do it by looking at the increasing or decreasing behavior. So here I will have a max, and I'll also have a max here. The x values will be -4 and -2, where these maximum occurs. And it just so happens, although this is not necessarily always the case, that they have the same value, right? This value and this value here, right, are both 6. What about the relative minimum? Well, here it goes from decreasing to increasing. And so right here, we're going to have a minimum at the x value of -3. What is the value of that minimum? It is +1. And that would be how we would break this one down. This one is a bit of a trick question, because if we pay attention to where it's decreasing all the way to here. Here it seems to sort of level off for just a moment, but then it starts decreasing again here. And so there is no switch. There's no place at which it was ever increasing to give us our relative min or max. So there's actually not any answer to these questions. There is no relative max and min on this graph. And as such, we would just put empty symbols or DNE or no solution, however they like that. This is all meaning the same thing here. 22 asks us a similar question about this slightly spikier fellow, but still we're going to answer it the same way. We notice that we have increasing behavior on these two segments, positive slopes. We have decreasing behavior on these two segments with their negative slopes. And as such, when I look for my maxima, that's going to be right here at an x value of 0. Its highest point is a 3. And my minima are going to be here and here. That's at -1 and +1 at the value of -2. These next questions are questions about symmetry. Symmetry means that something is unchanged when we perform some kind of operation on it. The ones we're going to be interested in are the kinds of symmetry where I am interchanging x with -x. If I do that, if I replace x with -x, and yet my y value stays the same, this is y-axis symmetry. If, on the other hand, I were to take a value of y that matched a certain value x and plug in -y instead, and if this relation, and it wouldn't be a function, of course, were to give me the same value of x, well, then this would be x-axis symmetry. One final way that we're going to be testing for symmetry, although there are many symmetries, it's its own entire topic of mathematics, is what happens if I change the sign of both x and y. If I have a given value x, and I change that to -x, and instead of being at y, I find myself down here at -y, then really what I've wound up doing is rotating by 180 degrees. We call this rotational symmetry, or 180-degree rotational symmetry, with respect to the origin, meaning that we rotated by 180 degrees around the middle point. Now, because we're not going to deal with any other kinds of rotations, they simply call this origin symmetry in this text, and I'll abide by that, although I think it's a gross oversimplification. There's a kind of simplification dealing with rotations by any angle. There's other ways that we can be symmetric around the origin. So let's not worry about that too much. Let's instead just regard this idea. If I change from x to -x, do I go from y to -y with my points? Or do we have some other kind of behavior? If I change from x to -x, does y stay the same? Or when I change from y to -y, does x stay the same? These kinds of tests are what we can do, and they actually have certain names as far as some of these symmetries are concerned. This is what is known as even symmetry. And this one over here is what is known as odd symmetry. If we look at the symmetric properties of polynomials, we'll see why this kind of even and odd terminology is used. For now, let's just perform a test. What happens when I plug in -y here? What do I get? Well, -y squared is just y squared. +7, that's what we started with. This is just x. So what we can see is that if I quote unquote plug in y, and here I'm treating x as a function of y instead of the usual way around, but when I plug in minus y, I wind up with the same x value that I started with. So this is definitely going to have x-axis symmetry. Another test that we can perform is to plug in a negative x value, but we need to rewrite this first as a function of y, like as y is a function of x. So let's do that. If I have x equals y squared plus 7, then I want to minus 7 from both sides. And then taking the plus minus square root, we wind up with the following two functions. Of course, y is not a function of x. It's a relation, right? Because we have these two values. And so we could look at what happens when we plug in negative x into here. You could even imagine plugging in an actual number like 1 or negative 1. Or if we wanted to stay in the domain, how about 7 versus negative 7? Well, this would be 0, and this would be a complex number. And so as such, they are not equal to one another. And therefore, we know it has no y-axis symmetry. And likewise, we could rule out origin symmetry as well. This next one says, determine the graph of the equation below, whether or not it's symmetric with respect to the x-axis, y-axis, or origin, or none of these. So let's actually just investigate what happens when we plug in different kinds of things here. What happens when I plug in negative x? Well, if I plug in negative x and I leave everything else the same, then we wind up with x squared minus y cubed, and that's actually exactly what we started with. And so as such, we know the relation that this difference is still 10 still holds. On the other hand, if I plug in minus y, then I would get x squared minus y cubed, and this would give me x squared minus negative y cubed, right? Because negative 1 times itself 3 times is negative 1. But hang on, that's x squared plus y cubed. That's not what we started with. So we don't know at all that that's equal to 10. We're kind of out of luck here. So what have we extracted? Number one, that it has y-axis symmetry, and that it does not have x-axis symmetry. Let's actually graph this equation with Desmos and see if we can spot the symmetry by looking at the graph. One of the really nice things about Desmos is that it doesn't require function inputs. It can take this kind of implicit form of two-dimensional polynomials and give you a graph for that, which is really quite beautiful. So let's take a look at our graph. As we can see, it's reflected over the y-axis. It is not reflected over the x-axis, right? If you plugged in minus y here, and here you can see what reflection would look like. It would look like this, but those two graphs don't match. On the other hand, when I plugged in negative x, those graphs absolutely did match. Here, maybe I can make this a little more like substituting in, although of course we do get the plus here. What happens if I plug in negative x? Well, we just saw that squaring it makes it positive, and so we just get what we started with. What happens if I plug in negative y? Well, squaring it makes it positive, and so we just get what we started with. And that's clear looking at the graph of a circle. You can reflect it over the y-axis, you could reflect it over the x-axis, you could turn it 180 degrees, and everything is still lining up with the circle exactly. Here we have a graph. They want to know if it's even, odd, or neither. And the main idea is, does it have y-axis symmetry or 180 degree symmetry rotated around the origin? That is even and odd symmetry respectively. Well, here you can see it has even symmetry because it is exactly a mirror image over the y-axis of itself. And so we would say this function is even. But it's not odd, or else it would have to have a reflection down here instead. It would have to look as if you had taken one quadrant and rotated it 180 degrees into the other quadrant. That's not what we see, and so this does not have odd symmetry. It has instead even symmetry. Here we have the three kinds of symmetries that we will be asked to identify in terms of even, odd, or neither. This is even because it is reflected over the y-axis. This is neither. It's not a rotation around the origin, nor is it reflection over the y-axis. This one, however, is. This is rotation. This point gets rotated 180 degrees to down here, and this gets rotated 180 degrees to up here. It's as if we took this half of the graph and spun it 180 degrees and pasted it onto the other side. So this is precisely what odd symmetry will look like in a graph. Okay, moving on. Here's where we're going to get a nice look about why they called it these things, right? If I plug in negative x to this, what is minus x? Well, we're going to have 5 times minus x x to the third power. And this is precisely minus 5x plus x to the third. But wait a minute, that's reversed the sign of both of these. So this is negative f of x. If you plug in a negative x and you get the negative y value back, then what you're looking at is an odd function. And notice that the powers of each of these are odd numbers. Likewise, on this one, if I take into g of x and I substitute negative x, then what I wind up with is 5 times negative x to the fourth power plus 4 times negative x to the second power. But that's a negative number raised to an even power is positive, right? Because we'll have pairs of negatives times each other, each one becoming positive. And so this is 5x to the fourth plus 4x squared. But wait a minute, that's exactly what we started with. There's not even a sign difference. If you plug in negative x and you get that precise y value back, g of x, that we expected to get when you plugged in positive x, well, this is y-axis symmetry, which is an even function. On the other hand, if we plug in negative x here, then we get a completely different function than what we started with. If I took a look at the graph of h of x, it would look like this. But if I said, what is h of minus x? This would be the square root of minus x, which is defined on the negatives rather than the positives. And that would be over here on this side. I'll even put it in a different color for emphasis. This is h of negative x. They are in fact not the same. When we test symmetry, we test if we get the same thing having plugged in two different numbers, usually negatives. And here we can see we do not get the same thing. We get a very different graph indeed. And so as such, this is neither. And the power here, x to the 1/2, is neither odd nor even. Let's go through and identify all of these functions from the function library. By the way, it would be a good idea to know at least how to graph the simplest versions of each one of these, but let's identify their symmetry quickly using their graphs. This function is neither the same on one side or the other, reflected over the y-axis, nor do we actually get symmetry by rotation, because we need to rotate around the origin, which would give me a very different line indeed. So this is actually neither. Lines have odd symmetry if they pass through the origin, and only if they pass through the origin. If a line doesn't pass through the origin, it does not have odd symmetry. And the only way that a line has even symmetry is if it is a constant line, which brings up an interesting point. Can something be both odd and even? Yes, the 0 line is odd and even. It's even because it's reflected around the y-axis, and it's odd because it is 180 degrees symmetric around the origin. So unlike numbers, functions could be both odd and even, although this is, I believe, the only function which is both odd and even. What about the cubic function? This is x cubed. Notice that it is 180 degrees symmetric around the origin, and as such is odd. If you plug in x versus negative x, you get the negative value for y. So we would say f of negative x was equal to negative f of x in this case, and that is what it means for a function to be odd. We could do this explicitly with f of x being equal to the cubic function. F of negative x is negative x to the third, which is negative x to the third, which is indeed negative f of x. Here we have the constant function. It is even because reflected over the y-axis, we get the same function back. Here we have the square root function. It is neither, because reflecting it over this axis gives me a brand new function, as does rotating it by 180 degrees. Neither of these give us the exact function that we started with, and as such, this is neither odd nor even symmetric. The absolute value function is reflected over the y-axis and as such is even. This is the same with the quadratic function. All squares are even. The identity function, this particular special line, is odd. Notice that if we plug in, say, 3, we get 3. But if we plug in -3, we get the negative of the original output at -3. So this has 180 degrees of rotational symmetry. It is odd. What about the reciprocal function? Well, take a look. I mean, if I plug in -1, do I get minus of what I started with? Yes. If I plug in 2, do I get minus a half? Yes. This is 180 degrees rotated around the origin and as such has odd symmetry. We could verify that explicitly by saying let f of x be equal to 1 over x, that's the reciprocal function, and then asking the question, what happens when I plug in -x? I get 1 over -x, which is the same thing as -1 over x, which is the same thing as negative f of x. So it satisfies the definition of an odd function in that sense as well. What about the cube root function? Well, the cube root function is odd because it has 180 degrees of symmetry in this sense. Now, if I wanted to see that explicitly, I could define f of x to be the cube root of x. If I said what then is f of -x, it's the cube root of -x. But wait a minute, this is -1. What's the cube root of -1? It's -1. And as such, out of odd indexed radicals, you can pull a negative sign, which gives us negative f of x again. This thing is odd. We're now going to pivot into graphing piecewise functions. The trick to doing this is to simply follow the rules in the intervals where those rules apply. We need to then investigate what those rules are and where they apply. Here, we're looking at negative x's. X is less than 0. And when we're in that region, it's going to look like the line -x minus 2. To graph those rules, I'd like to go to -2 and draw the line that has -1 for its slope. That would be either over 1 down 1 or back 1 over 1. But either way, we would get this line in general. Now I'm drawing it with a dotted line because I want to be cautious about where this rule applies. Right? We actually saw that there's only going to be a certain place where we're going to have this actual line. This is true when x is negative, not even when it's 0. And so what we would do is leave this as an open circle and firmly draw with a solid line the line in this region. We would ignore its values when we were not less than 0. In the same way, if I went to the second set of rules, let's graph them in blue. This is true for when x is positive or 0. So when it's positive or 0, it looks like 3x plus 3. That goes through the point 0, 3, and it has a slope of 3, meaning it goes over 1 and up 3. So passing through this point and over 1 up 3 thereafter, we get this line. It does extend this way too, but we don't graph that, and it's not part of our function because this rule set only applies to positive x's, not these negative x's here. So taking a step back, this is indeed our function f of x. It looks like these two lines separated by this gap. Now they ask us to evaluate certain things. They say, what is the range of f? Well, we can see that the lowest that it goes is actually going to be at -2. And it rises through all these other y values larger than that. The lines keep going up and up. And so we would say that the range of this function goes from -2 up to infinity. We wouldn't include the -2 because this is an open circle here. But all of these other y values are part of our range. Notice the domain is the entire real number line because these rules cover the entire real number line. These the negatives and these everything else. What is f of 2? Well, to evaluate f of 2, we don't even need the graph. What we need to do is take a look at the rules and say, well, for which one of these intervals will we find 2? X is less than 0 or x is greater than or equal to 0? Well, 2 is greater than or equal to 0. And that means we should use these rules to evaluate f of 2. F of 2 will in that case be equal to 3 times 2 plus 3, which gives me 6 plus 3 or 9. So here we have a 9. Here we have a slightly more complicated piecewise function. We have rules for when x is below 2, when it is equal to 2, or when it is greater than 2. That's all the numbers on the number line by a property called trichotomy. That tells us that the domain is all real numbers. But what is its range? To see that, we're going to have to graph this function and see what its behavior is on each one of these intervals. Let's start with x plus 4. The way I like to do these is by imagining what it would be if I plugged in 2. If I plugged in 2 here, I'd get 6. And so we would almost be going through 2, 6, but not quite, because that means, this less than means we're not actually plugging in 2 at that point, but we are going to get close to it. So let's actually plug that in and see where it goes. Here I go to 2, I'd go up to 6, and make an open circle. Now what? Well, we know we're talking about less than 2, so let's go backwards. This is a positive sloped line. Positive sloped line. So that means if I go backwards, we're going to be going down by 1. If this doesn't make sense, imagine if I went forward by 1 here, which is the usual orientation of slope, then we would be going up by 1, and we would get this positive 1 slope. So we need to draw this function as increasing, but since we're drawing it going to the left, we need to draw our graph like this. Now, this graph is true for all of the values less than 2. It just keeps on going, so we just let this graph keep on going. What about at 2? Well, at 2, it has a value of 2, so we would shade this point with a dot. And then what about greater than 2? Well, here we have x minus 4. Plugging in 2 here, I would get negative 2. We're going to put an open circle there because it really wouldn't be that point exactly. We're not going to plug that point in. This is a strict inequality, but we are going to get right up to it. So we do have to think about where that endpoint is. Now, this has a slope of 1, so let's go over 1, up 1, and that actually creates our line. If we just keep going over 1, up 1, we get the line there on out. So here is a graph of our piecewise function. What is its range? Well, you can see it's actually going to hit every y value. If I take a look at all of the y values hit by this graph, it's this and everything less than it. If I take a look at this one, I hit 2, but that was already covered. If I take a look at this one, it hits this and everything greater than it, but that shades in this circle and keeps on going with it. And so the range of this graph is actually going to be negative infinity to positive infinity. It includes all of the y values for some value of x. Now, what is the value at 2? Well, they actually gave us an explicit rule for that. They said, look, if you plug in 2, your function gives you a 2 back. So this is just this 2 right here. All right, let's go back to considering increasing and decreasing on this piecewise function. Let's go through and mark the increasing regions. That's here and nowhere else. So this looks to me at negative 10 up to 7. Negative 7. And we don't include those. We are increasing on open intervals only. I'm never increasing at this endpoint because he's actually not going up after that. He's just frozen right there. So we exclude those endpoints when talking about increasing, decreasing, and constant behavior. Likewise, here, I am decreasing, and I'm also decreasing here. So we would say we are decreasing from negative 7 up to negative 4, and we are decreasing from positive 5 up to positive 9. Where is the function constant? It's constant on this interval here. And as before, we do not include this endpoint. Even though it is defined at that bend, it has a function value, we wouldn't say it was increasing, decreasing, or constant at those bending points. So no bends, no endpoints, we exclude those, and we would say this thing is constant between -2 and 5. Now, the domain of this function will be the x values for which this has some defined value. When would that be? Well, it would actually not have a defined value here, but all these would, and including this one, because it is defined here at this point. Then it would continue on until we got to -4. So we don't need to break things up around this closed circle because it includes all the values in between these two open circles. But it skips this region from -4 to -2 and continues on. This bend has a defined point. So we could put a closed circle there, but we need not. We're just going to continue on until we get to 9, but there is no defined value there. It's an open circle, so we put an open circle. Now, what have I graphed as far as this interval is concerned? I've gone from -10 up to -4. Then there's a jump to -2, and then it goes all the way up to +9 and closes. All right, that's going to be it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.